Hello, my name is Serrano, and this is a friendly introduction to support vector machines, or SVM for short. This is the third of a series of 3 videos on linear models. If you haven't, take a look at the first one. It's called linear regression, and the second one called logistic regression. This one builds up a lot on the second one in particular. And I'll start with the credits. This year I taught a machine learning class at Quest University in British Columbia, Canada, and I had a wonderful group of students. We had an awesome time. Here's a picture of us with my friend Richard Hoshino on the right. He's also a professor. And actually, my students were the ones who helped me figure out the key idea for this video. So SVMs are a very important classification algorithm. And basically what it does is the usual. It tries to separate points of 2 classes using a line. However, it tries really hard to find the best line. And the best line would be the one that is sort of the farthest from the points as possible, the one that separates them best. Normally, SVMs are explained in terms of either some kind of linear optimization or some kind of gradient descent. What I want to show you today is something that I actually haven't seen in the literature. It may exist, but I haven't seen it. And it's a method that is a small gradient descent step-like method, which is sort of an iteration. And in this iteration, what you do is you first of all try to find a better line that classifies the points, and then at every step you just take 2 lines parallel and just kind of stretch them apart. Let me be more explicit. So let me start with a very quick recap on the previous video on logistic regression and perceptron algorithm. Basically what we want to do is we have data split into 2 classes, red points and blue points, and we want to find the perfect line. This is the perceptron algorithm. So what we want to do is not just find the perfect line, but a line with a red side and a blue side that splits the point in the best possible way. And the way we did this was we start with a random line, and then we start asking the points what can they tell us to make our line better. So for example, this point over here says I'm good, so don't worry, don't do anything. This blue one says, well, I'm on the wrong side, so you better move closer to me in order to classify me better. So we move a little closer. Remember that machine learning, we want to do tiny steps. We don't want to make any big drastic steps. So we ask another point. This one is red in the red area, so it says I'm good, don't do anything. Then we ask this one over here, and it says get over here, so we get over there. Then we ask this blue one in the blue area, so it says I'm good. By the way, we're grabbing random points here. There's no particular order. Then we ask this one, it's a red point in the red area, so it says I'm good. We ask this point, which is a blue point in the red area, so it says get over here. So we move closer. Then we ask this red in the red area, so it says I'm good. Then this red, which is now misclassified, is on the blue area, so it says move over here, and we listen to it, and now it seems like all the points are good. So that is, in a nutshell, the perceptron algorithm. I'd like to remind you that the way we did it is we started with a random line with red and blue sides. Then we picked a large number, the number of repetitions or epochs, which in this case is going to be 1,000. That's the number of times we're going to repeat our iterative step. Then step 3 says repeat 1,000 times. We pick a random point. We ask the point if it's correctly classified or not. If it's correctly classified, we do nothing. If it's not correctly classified, then we move the line a little bit towards the point. And we do this repeatedly, so we get the line that separates the data pretty well. So anyway, that was a small recap of the perceptron algorithm. And this algorithm is going to be very similar, but it's going to have a little bit of an extra step. So let me show you that extra step. First, let's start by defining what is it that the SVM does best. So I'm going to give you an example of some data here, and I'm going to copy it twice. And this is a line that separates this data, and this is another line that separates that data. So question for you, which line is better? So feel free to think about it for a minute. I think the best one is this one on the left, and this one on the right is not so good. Even though they both separate the data, if you notice, the one on the left separates the points really well, like it's really far away from the points, whereas the one on the right is really, really close to 2 of the points. So if you were to wiggle the line on the right around, you may miss one of the points and you may misclassify them, whereas the line on the left, you can wiggle it freely and you still get a good classifier. So now the question is, how do we train the computer to pick the line in the left instead of the line in the right, because if you remember, Perceptron algorithm just finds a good line that separates the data, but it doesn't necessarily find the best one. So let's rephrase the question. What I want to do is not just find one line, but find two lines that are as spaced apart as possible from each other. So here, for example, centered on the main line, we have these two parallel equidistant lines. And notice that for this case on the left, we can actually have them pretty far away from each other. On the other hand, if we do this with the line on the right, the farthest we can get is two lines that are pretty close. So we're going to compare this green distance over here with this distance over here. And the one on the left is pretty wide, whereas the one on the right is pretty narrow. So we're going to go for wide. So we're going to tell the computer, when you find a wide one, you're good. But if you find a narrow one, then you're not good. And now the question is, how do we train an algorithm to find two lines as far apart from each other that are parallel that still split our data? So this is what we're going to do, very similar to what we did before. We're going to start by dropping a random line that doesn't do a very good job necessarily. Then we draw two parallel lines around it at some small random distance. And then what we're going to do is we're going to do something very similar to the Perceptron algorithm. We're going to start listening to the points and asking them what we need to do. So let's say one point tells us to move in this direction, so we move in this direction. And then what we're going to do is at every step, we are going to separate the lines just a little bit. And then we listen to another point that maybe tells us to move in this direction. And then again, we're going to separate the lines a little bit. And then again, another point tells us to move in this direction. And then we're going to separate the lines a little bit. And that's pretty much it. That's what the SVM algorithm does. Of course, we need to go through some technicalities. One technicality is how to separate lines. So let me show you how to separate lines using equations. So let's say we have a line with equation, for example, 2x plus 3y plus minus 6 equals 0. And again, recall that we're living in the Cartesian plane, where the horizontal axis is the x-axis and the vertical axis is the y-axis. So notice that this line is the set of points that satisfy that 2 times the x-coordinate plus 3 times the y-coordinate minus 6 is equal to 0. What happens if I multiply this 2, 3, and minus 6 by some constant, for example, by 2? I get, for example, 4x plus 6y plus minus 12 equals 0. What line do you think this is? It's actually the exact same line, because any point that satisfies 2x plus 3y minus 6 equals 0 also satisfies that 2 times that thing equals 0, because 2 times 0 is equal to 0. So in particular, we get the same line. And if I multiply this equation by any factor, for example, by 10, I get 20x plus 30y plus minus 60 is equal to 0. I get the exact same line. So this line actually represents a family of equations. I can also multiply it by numbers that are smaller than 1. For example, 0.2x plus 0.3y plus minus 0.6. That's dividing the original equation by 10. That also satisfies the same line. And I can even multiply it by negative numbers and it still works. But now, let's see what changes. So here again, we have 2x plus 3y plus minus 6 equals 0. And the exact same line, which is 4x plus 6y plus minus 12 equals 0. Now, let's actually draw the line 2x plus 3y plus minus 6 equals 1. And 2x plus 3y plus minus 6 equals minus 1. Because what we're going to do is our two parallel lines to the original one are the ones with the same equation, except the ones that don't give 0, but they give 1 and minus 1. Now, what do you think happens if I do the same thing on the graph in the right? And this is important, so actually feel free to pause this video and think about it for a minute. I'll tell you what happens. What happens is that we get two lines that are parallel, but much closer. So the equations 4x plus 6y plus minus 12 equals 1 and minus 1 are actually a lot closer to the original one than the ones with equation 2x plus 3y plus minus 6 equals 1. And actually, if I multiply this equation by a smaller factor, for example, by dividing by 10, so I get 0.2x plus 0.3y plus minus 0.6 equals 1 and minus 1, then I get lines that are much more far away from the original one. And if I were to multiply it by a huge number, by 10 for example, I get 20x plus 3y plus minus 60 equals 1 and minus 1, then the lines get much closer. So the original line stays the same if I multiply by a constant, but these two parallel lines move farther away or closer depending on if I'm multiplying by a number that is close to 0, a small number, or by a large number. This is not going to appear in this video, but if you multiply by a negative number, the two lines actually switch. But this is not so important for this algorithm. But basically what we're going to do is we're going to be able to separate lines by multiplying them by a small number. That's really what we're going to do in this algorithm. But first we need some justification. Why is it that this phenomenon happens? So let's look at this line. For example, 2x plus 3y plus minus 6 equals 0. And let's just look at one side of it. So 2x plus 3y plus minus 6 equals 1. So why is it that this line over here in between is the equation 4x plus 6y plus minus 12 is equal to 1? It's actually exactly in the middle. Well, let's take a look at this equation. 4x plus 6y plus minus 12 equals 1 is the same line as if I just divide the entire thing by 2, including the 1. So if I were to divide 2x plus 3y plus minus 6 equals 0.5, I get the exact same line. And the reason is that any x and y that satisfy 4x plus 6y plus minus 12 equals 1, they also satisfy 2x plus 3y plus minus 6 equals 0.5. They're the exact same equation. So when I bring back this equation, well, now you can see that its value of 0.5 actually lies right in between the value of 0 and the value of 1. So that's why this equation is in between. And you can see that this works for pretty much any constant that I multiply the line by. So what we're going to do is we're going to introduce something called the expanding rate. And the expanding rate is very simple. We have again our equation 2x plus 3y plus minus 6 equals 0, which gives us this line. And then we have our two neighbor equations, the one that gives us 1, which is over here, and the one that gives us minus 1, which is over here. And our expanding rate is just going to be some number. And remember that in machine learning, we always want to make tiny steps. We don't want to make any big steps. So we want to separate these lines, but by very little amount. So we're going to take a number that is very close to 1, for example, 0.99. Let's say that's my favorite number that is close to 1. And we're going to call that the expanding rate. And what we're going to do is we're just going to multiply all these numbers here by 0.99. So what do we get? Well, we get these equations. The equations are 1.98x plus 2.97y plus minus 5.94 is equal to 0 to 1 and to minus 1. And these equations give us three lines. The one in the middle is still the same one, but the two on the sides are actually just a little spread apart. So we're just going to add that step to the perceptron algorithm, and that's going to spread our lines apart a little bit every time we iterate. So now we're ready to formulate the SVM algorithm, and it's going to be very similar to the perceptron algorithm. Step 1 is we're going to start with a random line and two equidistant parallel lines to it. And I'm going to color them red and blue just to emphasize which side of the line is red and which side of the line is blue in order to see which points we have correctly or incorrectly classified. Now step 2 is going to be pick a large number, the number of repetitions or epochs, the number of times we're going to iterate this algorithm. Step 3 is going to be pick a number close to 1, so the expanding factor. And we saw it's going to be 0.99. We can pick anything, but that's the one I'm going to pick close to 1. Step 4 is now the loop. So repeat 1,000 times, pick a random point. If the point is correctly classified, for example, this one says I'm good, then we do nothing. If it's incorrectly classified, then, for example, like this one, which is a blue point in the red area, it says get over here, so we move the line towards the point. So we learned in the previous video how to move a line towards a point like this. And then we're going to do the extra step, which is separate the lines using the expanding factor. So we're going to do separate the lines a little bit. And we're just going to repeat this many times, 1,000 times, until we get a pretty good result. And then we enjoy the lines that separate the data best. So notice that the two steps that we've added is this step 3, pick a number, the expanding factor close to 1, and the one where we separate the lines using the expanding factor. The rest is pretty much the same thing as the perceptron algorithm. So now, just for full disclosure, if you want to code this, like this is actually the perceptron algorithm that we saw in the previous video, where we added step 4 is the mathematical step where we check if something is in the blue and red area by checking if the equation applied on the point p comma q is bigger than 0 or less than 0. So we update the values of a, b, and c accordingly by adding the learning rate times the coordinates of the point. So the SVM algorithm is actually very similar. What we do is we start with a random line of equation ax plus by plus c equals 0, and we draw the parallel lines with equations ax plus by plus c equals 1 and minus 1. Then we pick a large number, the number of epochs, which is going to be 1,000. Then we pick a learning rate, which is going to be 0.01. We saw that in the logistic regression video. Then we pick an expanding rate, which is going to be 0.99. It's a number close to 1. And then the loop step is repeat 1,000 times. Pick a random point. If the point is correctly classified, then do nothing. If the point is blue in the red area, then we update the values of a, b, and c accordingly. If the point is red in the blue area, we update the values in a different way. And then as a final step, we multiply the values a, b, and c by 0.99, which is the expanding step. And again, the two new steps are step 3 and the expanding step. So that's it. That's the SVM training algorithm. I encourage you to code it and see how it does. Try different values for number of epochs, learning rate, expanding rate, etc. And let me know how it went in the comments. So that's the SVM algorithm. As I said, I encourage you to code it, take a look at it in some data sets and see how it goes. However, this comes out of somewhere. This comes out of an error function development with gradient descent. So now I'm going to show you what the error function is. And it's very similar to the perceptron algorithm, where we had a classification error based on how far the points are from the boundary. However, now we're going to have another thing that adds to the error, which is based on how far away these two lines are. So let me show you. So to start with the error functions, let me first ask you a question. Here we have the same data set twice, and I'm going to show you two support vector machines that classify it. The first one is this one, and the second one is this one. Now, the question is, which one do you think is better? Feel free to pause the video and think about it. So notice that the model on the left has one problem, which is that it misclassifies this point. However, it's good because it's got the lines pretty wide apart. The model on the right is great in terms of classification because it classifies every point correctly. However, the lines are very close together. So the question is, which one is better? And the answer is, we don't really know. It depends on our data, it depends on our model, it depends on the scenario. But with error functions, we can actually have an approach to maybe analyze what exactly do we want. So let's recall what happened with the perceptron error. So here we have some points and a model, a perceptron that separates them. Now this one makes some mistakes, right? It makes these two because these two are blue points in the red area, and makes these two because these are red points in the blue area. So the question is, how do we measure the error, or how bad this model is? And the rationale is, if a point is on the correct side, then its error is 0. If a point is on the wrong side, then the error can change. If a point is close to the boundary, then the error is small, and if it's far from the boundary, then the error is huge, because if you're, for example, a blue point and you're close to the blue area but still in the red area, you have a small error. But if you're well into the red area, then you generate a lot of error because that model is very wrong on that point. So what we want is the distance, or not exactly the distance, but something proportional to this distance. And same here. So we're going to add a number proportional to these distances, and that's going to be the perceptron error. So for SVMs, it's going to be similar. We're going to have our lines, and now we're just going to have two classification errors coming from different places. So what we're going to have is a red one. So our red area now doesn't start from the middle, but it starts from the bottom line. And every point above of this line that is blue it's automatically misclassified. So these three are misclassified. And the error is precisely the distance from the bottom line. And that's simple. So notice that this blue point that is close to the bottom line is actually misclassified, even though it was correctly classified in the Perceptron algorithm. This is okay. It's a harsh error function. Now, the blue error comes from the line in the top. So it comes from here. Now, every red point underneath this top line is going to be misclassified. And its error is going to be similar to the Perceptron error. It's going to be proportional to this distance over here. So we're adding all those distances, and that's our error. So those two errors form the classification error. Now we have something called the margin error. And the margin error is simply something that tells us if these two lines are close by or far apart. I'm going to be a little more specific later, but it's basically a number that is going to be big if the lines are close together and small if the lines are far apart, because it's an error. So the better our model, the smaller the error. And the better our model, the wider our lines are. So let's actually look a little bit more at the margin error here. So we have our data set and our data set again and the two models. So this one has the lines pretty far apart. Therefore, it has a large margin, so it's going to have a small margin error. And this one over here, the lines are pretty close, so it's got a small margin. Therefore, it has a large margin error. And just to show the contrast, notice that this model on the right has a small classification error, and this model on the left has a large classification error, because the model on the right classifies all the points correctly, and the one on the left classifies the points one point incorrectly. But let's get back to our margin error. So we have our three lines, and let's recall the equations of the lines are something along the lines of ax plus by plus c equals 1, and ax plus by plus c equals minus 1. So now we're going to have to do is calculate this distance. So that I'm going to leave as a challenge for you to do some math and show that this distance is actually 2 divided by the square root of a squared plus b squared. So I challenge you to prove this. What you have to do is play with linear equations and the Pythagorean theorem. And so now the question is, what can our error be? So let's think about it. We need a number that is big if the distance is small, and a number that is small if the distance is big. So what can our error be? Feel free to think about it. The hint is, look at the denominator, right? The bigger a squared plus b squared is, the smaller this number is, and vice versa. So what about just taking the margin error to be this, a squared plus b squared? Notice that if this number is large, that means the denominator is small, and vice versa. So if we let our margin error just be that sum of squares, that works. That actually measures how far apart the lines are in the opposite way. So if the lines are close, the error is big. If the lines are far, the error is small. If that looks familiar, shouldn't be a surprise. This is actually the regularization term, if you've seen L2 regularization. So now we can summarize where SVM error is. Here it is. We have our data set and our model, and the error basically splits in 3. First is the blue classification error, which is basically measures all the red points that are in the blue side. Then we have the red classification error, which measures all the blue points that are in the red side. And then we have the margin error, which measures how far apart the lines are. So the red and the blue get together to form the total classification error, which tells us how many points are misclassified and how badly they are misclassified, and then the margin error that tells us if the lines are far apart or close by. And these two get together to form the total SVM error. So that is the error in a support vector machine, the one that we're supposed to minimize. And the gradient descent steps, very similar. What it does is actually the same thing as the SVM trick. What it does is, here we have our data, and here we have a model, and this model is pretty bad. Notice that the lines are pretty narrow, and it also misclassifies a bunch of the points. So this is a bad SVM. It's got a large error, both in the classification sense and in the margin sense. And what we want to do is, using calculus or using gradient descent, we minimize this error in order to get to a good place, a good SVM that has a good boundary, The lines are far apart, and it actually classifies most of the points correctly. So in the same way that we did with the perceptron algorithm, this gradient descent process takes us from a large error to a small error. And this actually is exact same thing as the SVM trick that I showed you recently of moving the line closer to the points plus separating the lines a tiny little bit. So now I have a challenge for you. And the challenge is simply to convince yourself that the expanding step actually comes out of gradient descent. So take a look at this. We have our lines with equation ax plus by plus c equals 1 and ax plus by plus c equals minus 1. And we have the margin over here and the margin error, which is a squared plus b squared. So if you're familiarized with gradient descent, what happens is that we want to take a step in the direction of the negative of the gradient. So the gradient is the derivative of the margin error with respect to the two parameters a and b. This is a very simple gradient because it's the derivative with respect to a is simply 2a, because a squared plus b squared, the derivative with respect to a is 2a, and the derivative with respect to b is 2b. Therefore, our gradient descent step takes a and sends it to a minus the learning rate eta times 2a, which is the derivative, and does the same thing with b. It turns it into b minus eta times 2b. Now we can factor this as a times 1 minus 2 eta, and the bottom one we can factor it as b times 1 minus 2 eta. But notice something here. Notice this number over here. This is exactly the expanding factor, because what we're doing is multiplying a by a number that is close to 1. Remember that we multiplied a and b by 0.99? This one here is a 0.99 because if we take eta to be a small number, then we're multiplying a by a number that is very, very close to 1, because if eta is small, then 1 minus 2 eta is very close to 1. So that is exactly the expanding step. So the expanding step is coming from gradient descent and using the regularization step. Anyway, the challenge is to formalize this and to really convince yourself that this is the case. So now let's go back a little bit and remember these two models, because we never really answered the question of which one is better. Remember that the one on the left misclassifies one blue point, and the one on the right just has a very, very short distance between the lines. So they're both good and bad in some way. So let's really study them. The one on the left has a large classification error because it makes one mistake, and a small margin error because the lines are pretty far apart. And the one on the right has a small classification error because it classifies every point correctly, and a very large margin error because the lines are too close by. So again, which one to pick depends on us. It depends on what we want from the algorithm. However, we need to pass this information to the computer. So we need to pass information of which one do we care more about, the classification error or the margin error. And the way to pass this information to the computer is using a parameter or a hyperparameter. This one's going to be called a C parameter. So recall that the error here is the classification error plus the margin error. So we're just going to take a number, C, and attach it to the classification error. And so now our error is not the sum, but a weighted sum, where one of them is weighted by C. And now what happens over here? Well, recall our error is the C times the classification error plus the margin error. So what happens if we have a small value of C? If we have a small value of C, then the classification error gets multiplied by a very small number, so it's all of a sudden is less important. And then the margin error is the important one. So we are really training an algorithm to focus a lot more on the margin error. So we end up with a good margin and maybe a bad classification. So we end up with the model on the left. However, if we have a large value of C, then C is attached to the classification error. So this means that the classification error ends up being a lot more important, and the margin error ends up being negligible if C is large. So therefore, the model with a large C focuses more on classification because it tries to minimize the classification error more than it tries to minimize the margin error. So we end up with a model like the one in the right, which is good for classification, bad for margin. And so again, we decide this parameter ourselves. What we really do in real life is try a bunch of different ones and see which algorithm did better. But it's good to know that we have certain control over this training. And these are called hyperparameters. Every machine learning algorithm has a bunch of hyperparameters that one can tune to decide what we want. So that's all, folks. Thank you very much for your attention. I remind you that this is the last of a series of 3 videos on linear models, linear regression, logistic regression, and support vector machines. So I hope you enjoyed this as much as I enjoyed it. Thank you. Remember to subscribe if you want to get notifications of more videos coming. If you like it, please hit a like, share it with your friends, or comment. I love reading the comments. I read them all. If you have suggestions on what other videos to make, I love to hear them. And if you want to tweet at me, this is my Twitter handle, Louis Likes Math. Thank you very much, and see you in the next video.